Hi everybody. Today my topics is second order linear differential equation. Before going to second order linear differential equation, let's look at general linear differential equation of nth order, which is in the form of like this one. For convenience of notation, the nth derivative with respect to the independent variable x can be denoted by d to the power n. Here d is called operator and it represents d by dx. In the first equation, left hand side, a0 to an to be considered either function of x or constant, and right hand side we can consider either 0 or m. Actually we get two types of equation. One is homogeneous and another is non-homogeneous. If right hand side m is equal to 0, it is homogeneous. If right hand side m is not equal to 0, then it is non-homogeneous. The general form of second order linear differential equation is like this one. You can see it here. And the equation can be written as this one, a d square y plus b dy plus cy equal to 0. Here d is the operator. And left hand side of the first equation, a, b, c to be considered as constant, and at right hand side equal to 0, it means this equation is homogeneous. Actually, we solve the equation number 1 to get general solution. Actually, general solution, it is also called as complementary functions, which always contains two arbitrary constant. And our target to get complementary functions or general solution from this type of equation, I mean second order linear differential equation. Here I want to mention an important point, and it is that the complementary function is a linear combination of two linearly independent solutions. If two solutions are y1x and y2x, then surely neither y1x nor y2x is a constant multiple of other. Here this example, fx equal to 2 to the power 2x and gx equal to x e to the power 2x is linearly independent because it is not a constant multiple of others. But the second one, fx equal to x cube and gx equal to 2x cube, it is a linearly dependent because it is a constant multiple of others. Or in other way I can say one is not simply a multiple of others. So to find complementary function, first we should have two linearly independent solutions in terms of y1x, y2x. Then we can form complementary function by simply adding constant multiples of the two solutions. Here c1 and c2 are arbitrary constant. So we can write complementary function as y equal to c1 y1x plus c2 y2x, this one. More details of it to be explored in Next slides. Now, to solve the equation of, this one, a second derivative plus b first derivative plus cy equal to 0. To solve this equation means we are looking for a function y such that constant a times its second derivative, constant b times its first derivative, plus third constant c times y equal to 0. Now, that's why considering the exponential function, it is very important points. Considering the exponential function in the first step is the best approach, because exponential function y equal to e to the power kx, here k is a constant, it has the property that, it is a special property, it has the property that its derivative is a constant multiple of itself. I am repeating the line again. It has a special property that its derivative is a constant multiple of itself. As an example, first derivative is equal to k e to the power kx, and as well second derivative equal to k square e to the power kx. Now, substituting all these in equation 1, what you get? We get this equation. Now, making common e to the power kx, equation takes the form as this one, like this. Here e to the power kx is not equal to 0. Here e to the power kx is not equal to 0, then y equal to e to the power kx is a solution of equation 1. It is a very important point to note. And also here k is the root of the equation, and right here you can say ak square plus bk plus c equal to 0 is the auxiliary equation, this one. And here one important point, this equation ak square plus bk plus c equal to 0 is an algebraic equation. We got this by replacing second derivative by k square, first derivative by k, and y by 1 from equation 1. Then we get this auxiliary equation, and we can see here ak square plus bk plus c equal to 0 is an auxiliary equation. It's the most important point for solving all the linear second order linear differential equation. We have like two roots of auxiliary equation, roots of auxiliations, and we can find roots in two ways. How? Number one is by factoring, number two is by using quadratic formula. Here quadratic formula as k1 equal to minus b plus square root of b square minus 4ac divided by 2a, this one, and it is same, only instead plus we wrote here minus. Now b square minus 4ac is called discriminant, and there is three cases. Case 1, b square minus 4ac greater than 0. So roots, in that case roots are real and distinct. And in these situations our general equation, general solution will be, complementary function will be c1 e to the power k1x plus c2 e to the power k2x. Here k1 and k2 are two roots. In case of case 2, b square minus 4ac equal to 0, it means roots are equal or repeated roots. Here equation will be c1 e to the power kx plus c2 x e to the power kx. Here k1 equal to k2 equal to k because roots are equal. When we go for case number 3, it is b square minus 4ac less than 0, roots are complex. Roots are complex. So what is happening here? In case of roots are complex, suppose we have two roots, k1 will be considered as alpha plus I beta, I is imaginary, k2 equal to alpha minus I beta, I also imaginary. This is the two roots. So in that case our equation will be e to the power alpha x bracket c1 cos beta x plus c2 sin beta x. This is the general solution for the equation which has complex, roots are complex in that situation. First example, to solve a second order linear homogeneous differential equation which is d square y by dx square minus 5 dy by dx plus 6y equal to 0. Here auxiliary equation appears as k square minus 5k plus 6 equal to 0. K square comes from second derivative, k from first derivative, constant 5, and y is 1, so 6 is here. So auxiliary equation is k square minus 5k plus 6 equal to 0. Here we can get the value of two roots by factoring, and by factoring we get k minus 2 and k minus 3 equal to 0. So k equal to 2 and k equal to 3. So we can say roots are real and distinct. So our two solutions are y1 equal to c1 e to the power 2x and y2 equal to c2 e to the power 3x. And the general solution, it is y equal to c1 e to the power 2x plus c2 e to the power 3x. It means summing up these two, we are getting general solution. And here if we compare with the case 1, it is b square minus 4ac greater than 0, and it shows here its value is positive 1, so greater than 0. So general solution will be c1 e to the power k1x, c2 e to the power k2x. So k2 and k1, if we compare with this 2 and 3, so general solution takes the form actually like this one. And this is also a complementary function. For our second example, to solve a second order linear homogeneous differential equation which is 5d square y by dx square plus dy by dx minus y equal to 0. Here auxiliary equation becomes as 5k square plus k minus 1. Same way, this k square comes from second derivative, k from first derivative, and value of y 1. We have to use quadratic formula to find roots of auxiliary equation. Here we shall use quadratic formula, and it is k equal to minus b plus minus square root of b square minus 4ac divided by 2a. Now putting the value of coefficient a, b, c, the formula we can write as this one. And using plus and minus sign, we get two roots. k1 equal to this with plus sign and k2 equal to this with minus sign. So the roots are real and distinct. Now comparing again case 1, b square minus 4ac greater than 0, it means it is positive. So here we got actually 21. So our general solution like this one. So if we go ahead and see, our two solutions are C1, this value is K1, and this one K2. This is K2, K1, and then summing up these two solutions, we get the general solution as this one. Comparing this one, it's same. And this equation, it is also a complementary function. Now for third example, to solve a second order linear homogeneous differential equation, which is d square y by dx square minus 4 dy by dx minus 21y equal to 0. Here actually we have to find general solution as well as particular solution of the given equation. First we are going to find general solution. Here auxiliary equation is k square minus 4k minus 21, and factoring the auxiliary equations, we get k minus 7 and k plus 3 are the two factors, and right away we can write two roots as k equal to 7 and k equal to minus 3, and it's very clear that roots are real and distinct. So easily we can write two solutions, and that is y1 equal to this and y2 equal to this. Now if we look at case 1, b square minus 4ac greater than 0, here we found it is hundreds. So general solution we have to follow same way. So summing up these two, we get the general solution as y equal to c1 e to the power 7x, this k1 means 7, plus c2 e to the power minus 3x, so this k2 equal to minus 3. So this, and this is also a complementary function. Now we have to find particular solution, but to find particular solution we have to use given conditions. What are the given conditions here? Here given conditions are the y equal to 0 and y equal to 2 when x equal to 0. If we put the value x equal to 0 on general solution, here 0, here 0, so e to the power 0, e to the power 0 equal to 1, so remains as c1 plus c2 and y value 2. So our equation, on general solution, if we put value, our equation will come like this. Now we have to put this value on its derivative. Derivative means we have to do first derivative of this, and first derivative of this equation will come like this one. Now if we put the value x equal to 0, the equation in terms of c1 and c2, it will come like this. Yes. Now solving these two equation, I mean this one and this one, we get the value of C1 and C2, 3 by 5 and 7 by 5. Now putting these values C1 and C2 in general solution, we get the particular solution as this one. For our fourth example, to solve a second order linear homogeneous differential equation, which is d square y by dx square minus 6 dy by dx plus 9y equal to 0. Here auxiliary equation is k square minus 6k plus 9 equal to 0. So after factoring, we find k minus 3 equal to 0. Here roots are k equal to 3, k equal to 3. It means roots are repeated. And now we can write two solutions as, I mean here two solutions as this one, y1 and y2. Now if we compare this with case 2, case 2 means b square minus 4ac equal to 0, and here we found the value, it is 0. So the general solution will be c1 e to the power kx plus c2 x e to the power kx. So same way, summing up these two, our general solution will be like this, c1 e to the power 3x plus c2 x e to the power 3x, and taking common e to the power 3x, it comes in this form. And this is also complementary function. Now for the, fifth example, to solve a second order linear homogeneous differential equation, which is d square y by dx square minus 8 dy by dx plus 20y. Here auxiliary equation is k square minus 8k plus 20. Same way, k square means it comes from second derivative, k comes from first derivative, here coefficient 8, y will be 1, then remaining coefficient 20. Now to solve this auxiliary equation, we use quadratic formula. And what is that? Here k equal to plus minus b plus minus square root of b square minus 4ac by 2a, and putting the value of b, a and c, we get the equation like this. Here there will be roots k1, 8 plus square root of minus 16, so it is negative, and k2 also it is negative, so we are considering it as a 4, and this is 2, and as it is negative, so we have to take here imaginary term with this 2. Due to this negative square root inside, there is a negative value. And since here roots are complex, we can see from here, because I value is there, imaginary term is there, so it is a complex term. Now this is actually case 3. How it comes? B square minus 4ac less than 0. So putting the value, we found it is minus 16. So of course it is less than 0. So we have to take k1 means alpha plus I beta. This is the thing. Alpha is 4, beta is 2. Again k2 equal to alpha minus I beta. So alpha minus I beta. Beta is 2. So here I wrote alpha equal to 4, beta equal to 2. So our two solutions will be y1 equal to c1 e to the power 4x cos 2x, and another one will be y2 equal to c2 e to the power 4x sin 2x. Summing up these two solutions, we get general solution c1 e to the power 4x cos 2x plus c2 e to the power 4x sin 2x. It is same as this one, same as this general solution. Now taking common e to the power 4x, we get c1 cos 2x plus c2 sin 2x. And this is also a complementary function. That's all for today, and thanks for watching.